Okay, so our fourth paper for this session is a Museum Exhibit Identification Challenge for the Supervised Domain Adaptation, and it will be presented by Piotr Koniusz.
Hi everyone, I'm Piotr. It's very nice to be here today. I'm a senior research scientist in Data 61 and CSIRO, and I'm also associated as a lecturer with the Australian National University. So today I'll introduce to you our new museum exhibit identification dataset, and I'll talk about our supervised domain adaptation approach. This work is a joint work with my PhD students Yusuf and Hongguang and my very good colleagues Mehrtash, Fatih and Ray. So to motivate this work, the results on the Office 31 dataset, which is typically used for domain adaptation, have reached 90% of accuracy. So we thought that we would like to give the community a challenge, and we propose Open Museum Identification Dataset to stimulate research in egocentric recognition, few-shot learning, domain adaptation. We have collected 866 unique exhibit labels, around 8,000 source and target images, and OpenMIC exhibits photos of paintings, timepieces, sculptures, glassware, and so on. Museums do contain some of the most visually diverse objects, and it's really hard to find the data on Flickr or YouTube from wearable cameras. We study artwork identification in the context of supervised, unsupervised domain adaptation, one and few-shot learning. So our source domain is very clean. We capture photos in a very controlled manner with the Android phones. Here we zoomed on each exhibit several times and took photos from different points of view. But for the target domain, the capture is in the wild. So essentially we use wearable cameras. We do not have control over the shutter. The objects themselves may be rigid, non-rigid. They might be emitting light. They might be in motion, or they might be small or composite installations. And at the same time, our target domain exhibits a lot of photometric and geometric distortions, such as extreme viewpoint changes, scale changes, glares. To give you more examples, for instance, here, pairs of images show within class variations, which are quite big for some of these exhibits. The hardest to identify instances in this data set are due to, for instance, small size of the objects or scene clutter. Occasionally, photos are taken from a distance from the exhibits. I wanted to explain what supervised domain adaptation is. So the idea is to take small or large number of source data points that are labeled and to transfer them to the target data, which is scarce, and it's also labeled. So ultimately, the goal is to beat the combined training on source and target and fine-tuning. And here we take the assumption that we don't want to do big data because the idea is to actually try to mimic brain-like systems that are able to learn concepts from few samples. The evaluation protocols that we propose here are training and evaluation per exhibition. So this is 10 experiments. Also training and testing on the combined set of all 866 exhibits. We also break down performance with respect to different scene factors, such as quality of lighting, motion blur, occlusions, and so on, to identify what is the most detrimental for the performance. And we also use the top KN measure here, which quantifies whether any of n ground truth labels are contained in top K predictions. So we want to be lenient towards the network if it's able to recognize at least one of the exhibits in the image. So perhaps the biggest challenge of all was to find enough USB ports to charge all these USB cameras before capture session. Our pipeline is built on the so-called SOHOT model that we proposed a year ago, and it employs the classifier loss L and the source and target alignment loss H. So essentially, it's a form of trade-off between within and between class statistics. It's very similar to linear discriminant analysis. For the alignment loss, the idea is to establish so-called commonality between class-wise statistics of source and target, and we perform partial alignment. So in figure A here, we try to separate positive and negative data points. Beta indicates uncertainty in how hyperplane should be fitted to separate these two classes. And of course, after alignment, it's clear in figure B that it's very easy to fit the hyperplane and separate these instances. However, figure C shows that we don't perform full alignment. We assume that source and target, they do have some data points that are indeed correlated, and it's good to align them. But also, the source and target have data, potentially source and target specific data that really cannot be aligned, and it doesn't make sense to force network to do so. For the pipeline, we have two streams, source and target. They produce lambda and lambda star features. We employ loss. L for classification, H is the alignment loss, and it performs alignment on the cone on symmetric positive definite matrices. So in figure B, to the top, you can see how the alignment is performed along the geodesic path for Riemannian geometry, and in figure B, we show how the alignment would be performed according to Euclidean geometry, where the reprojections are needed. And in figure C, this is our testing pipeline, where we cut off source and just use target network. So more specifically, our alignment loss depends on two sets of variables, phi star, one set per network stream. Feature vectors depend on parameters of the network, source and target that we optimize over. We form covariances from these features, means, and we plug them into the loss shown below, where we have the classification loss for the source, for the target, and also distance d that performs alignment between covariances of a given class. However, according to Riemannian geometry, Euclidean distance is suboptimal in alignment of covariances because there are positive definite matrices. So we investigated a fine invariant Riemannian metric, as well as Jensen-Bregman logged the divergence here. And the problem with these distances is that it's very hard to backpropagate through them because they require backpropagation through SVD. Typically, SVD is pretty costly for high-dimensional matrices. So the idea here is to exploit the low-rank nature of our covariance matrices and the fact that we have low number of data points per class. So for the typical n and star being in total 33 samples, we obtain very small covariance matrices, and it's much easier to backpropagate through this. We proceed as follows. We form a matrix of pivots Z by concatenating source and target features. We choose a linear kernel and we form a Nystrom projection. And we obtain square root of quadratic form of features here that turn out to be our projections pi and pi star. And a very nice property of this design is that it turns out that projection pi is isometric, so the two distances, whether they're evaluated on the covariances from features phi, or whether they are evaluated on the covariances from the projections, they are equal. So this is not an approximation, there's the isometric property there. For the backpropagation, after crunching maths, we obtain this matrix Z stroke that typically would require also backpropagation through that. It would depend on features, and it would require backpropagation through the square root of matrix. However, in this work, we have shown that Z is actually a rotation matrix, and by the design of Euclidean and Riemannian distances, they are rotationally invariant. And this implies essentially that we can treat Z stroke as a constant, which makes the whole process very fast and tractable in terms of backpropagation. So for the experiments, we have several baselines. So we train our algorithm on the source data, target data, source plus target. We also evaluate it with the alignment for the Euclidean distance. The challenge one essentially shows the results, which are the breakdown with respect to the 10 exhibition spaces. And aligning source and target statistics via JBLD distance is always better than just training on source plus target. Also, fine invariant Riemannian metrics tends to perform better, a little bit better than Euclidean distance. For challenge 2, the combined results show that we achieve around 64% accuracy here. So there is still some scope for improvement on this data set. Perhaps the most interesting is challenge 3, where we break down performance with respect to different photometric and geometric distortions in the images. And according to this table, the biggest challenge in recognition is when the objects are small, whether there is a pole light, or essentially when the images are blurred. In the colorful tables over here, we show a breakdown of performance with respect to pairs or triplets of factors. So the important message here is that, for instance, when the blur and small appearance of objects co-occur in the image, or glare and small, for instance, the results drop to 20%. So this is a message for domain adaptation practitioners that perhaps we should target some specific photometric geometric distortions to improve the performance. And lastly, challenge 4 is just an unsupervised domain adaptation, where we evaluated several different state-of-the-art algorithms, and the results here are around 50%. So there's still some way to go to reach 90. So just conclusion, we do propose a new challenging data set for domain adaptation and few-shot learning as well. We have interesting evaluation protocols here. We are able to backpropagate through a fine invariant Riemannian metric fast, which typically is a challenge. Our data set is available, so if you're interested, please do contact me. We also organize a workshop in ACCV on domain adaptation and few-shot learning, and we organize a challenge on this data set. So also please do contact me if you're interested. Other than that, please do see our poster for more details. Thank you.
We have time for one question. No question? All right. I have a question. So what is particular about the museum setting compared, for example, capturing street scenes with different kinds of cameras?
Sorry, I couldn't hear you well.
So what is particular about a museum setting compared to any other setting?
Well, we found that museum setting actually contains more challenging objects that you would normally find on, for instance, Flickr, which are human-centric, where every object is pretty much nicely centered. People tend to keep good quality photos, but with wearable cameras in a museum, we don't have control over that. So we have essentially challenging exhibits. For instance, imagine yourself some complex installation, some appliance, it's very hard to even capture the entire appliance within one photo. Or objects are translucent, they might emit light. Typically, computer vision does not focus on this type of objects because there's no such an abundance of them in everyday scenes. So I think that's it.
Okay, thank you very much. So let's thank the speaker again.